Hello, and welcome to South Pole, the podcast that explores everything Antarctica. I am your host, Clark Marchese, and today we're talking about astrophysics, astronomy, and cosmic research in Antarctica. All right, when I had the idea for a podcast about all things Antarctica, I did a little brainstorming session about what types of episodes to include, what types of topics to cover. I'm thinking penguins, explorers, icebergs, etc. One thing I did not have on my initial brainstorm list was astronomy and astrophysics. It was only until after looking deeper into all the scientific fields that do cool stuff down there that I found a network at the Scientific Committee for Antarctic Research called the AAA. Astronomy and Astrophysics from Antarctica Expert Group. And they're doing quite a lot of fascinating stuff. So today we're going to talk to one of the researchers from the astrophysics side of that group. And aside from learning what the difference is between astronomy and astrophysics, we're also going to learn why there's so much astro research near the South Pole. We're going to learn what a neutrino is, and we're going to hear about the longest standing research project on the Antarctic continent. We're also going to talk about the value of science whose purpose is simply to understand more about the universe we live in. And perhaps I should not have used the word simply because there's not much simple about astrophysics. Believe it or not, I really did not succeed in any science classes in high school, but physics was the science where I was really like, girl, what? Shout out to Sydney Morrison, who I sat next to, who I believe listens to this podcast and made sure I passed the class by helping me cram the day before or sometimes the morning of each exam without me having any conceptual understanding of the topic. In any case, you do not need to worry today if physics is not your strong suit either, because the guest I found, Dr. Jim Madsen, is a very skilled science communicator who uses a lot of helpful metaphors and analogies to hold our hands through the episode. Dr. Jim Madsen is a leading expert in astrophysical research and a prominent figure in Antarctic science. A bulk of his work involves the Ice Cube Neutrino Observatory at the South Pole, the actual South Pole, where he explores the mysteries of the universe through the detection of neutrinos from outer space. So without further ado, let's try and understand what all of that means, and let's get started. All right, Dr. Madsen, welcome to the show. The first question I have is if you could just introduce yourself and tell us a bit about your research.
Sure. I'm Jim Madsen. I was a former physics professor. Now I'm the interim director of the Wisconsin IceCube Particle Astrophysics Center at UW-Madison. We have a variety of experiments that people work on, but the primary one is a project called IceCube, which is at the South Pole and explores the universe in a whole different way, which I'm sure we'll get into.
So the Ice Cube is a research center at the actual South Pole, and I typically like to ask if guests have been to Antarctica, but I'm assuming then in your case the answer would be yes?
Yeah, actually, I've been 5 times. I work on 2 different projects in Antarctica, so 4 times to the South Pole and 1 time just to the coast. I've been working on IceCube and its predecessor, which was called Amanda. IceCube is just a funny name. Amanda stood for Antarctic Muon and Neutrino Detector Array, and it was a smaller version. And so I've been working on that one for about over 25 years. About a decade or so ago, I also got involved with a smaller project that was studying lower energy particles from space called cosmic rays. The IceCube is concerned with these particles called neutrinos. The lower energy project studies neutrons. That, interestingly, is the longest, the one that studies the neutrons. It's the longest continuously running project in Antarctica. So,
of any kind?
Of any kind, yeah. So when they first got the idea to have a station in Antarctica, after the International Polar Year, I think it was like 1955, 56, and then they started looking for what kind of projects they do. This was like the first project that's been in one form or another, collecting data continuously.
Wow, that's incredible. And also, maybe before we get into the nitty-gritty of the research, it might be good for us to understand what is the difference between astronomy and astrophysics?
So, it's one of these deals where it depends on where your interests lie. So astronomers, and I will try to say this in a way that doesn't offend astronomers, but astronomers are like catalogers. They go like this shape. Now let's count up how many galaxies that have this shape. And then we have, these stars, and then we see mostly these stars, and there's stars this color, and there's stars, and then the astrophysicists, what they try to do is understand from a fundamental standpoint why things are the way they are, and then what's the rules that govern the existence. So, for example, helium wasn't discovered on Earth. Each element has a unique set of colors it produces. And so astronomers, when they started doing those they call it spectroscopy, right? They saw a set of colors that couldn't be identified with any gas that had measured on Earth up to that date. And so helium was discovered in that way. So astronomers would take those tools and say, let's go and look for the helium and these other gases. The astrophysicists would be saying like, well, how come there's helium? And then what are the processes that produce the helium and so forth. So let me stop there and see if that makes sense.
Okay, I actually think I followed that. So then the next question is having to do with the fact that when I had the idea for this podcast about the South Pole, I didn't anticipate doing an episode about astronomy or astrophysics, but as it turns out, there's quite a bit of this type of research down there. So can you give us an overview of how these fields fit into Antarctica?
Yeah, the basic idea is, as you might guess, it's a challenge and not inexpensive to get to Antarctica. So you need to have some compelling reason, besides, wow, I would really like to go to Antarctica, to set up an experiment there. So there's kind of a few reasons that they would do it. So in our particular experiment, what was realized, it was the idea to look for these kind of messengers from outer space was actually proposed in 1960, but they knew that you needed a clear medium that was at least 1 kilometer by 1 kilometer by 1 kilometer. So that's why it's called IceCube, because we have a cubic kilometer of ice. But everyone thought, since clear and it's such huge volume, everyone just thought of water. And then about 1988, Francis Halston at UW-Madison came up with the idea maybe you could put light sensors in a chunk of ice. So our reason for being at the South Pole is there's a station that has electricity, places to sleep, people to feed you, logistic support to get stuff there, and there's 3,000 kilometers of ice. There's some other places that actually have thicker ice, right? But they don't have a station. So in our particular case, it was the ice plus the support. Other projects are based in Antarctica because you're at a higher altitude, because you're on top of this big ice sheet. And then the atmosphere is super clear. And if you're doing optical telescopes, it's dark 6 months out of the year. So there's advantages there. The other kind of really neat thing that goes on is there are balloon launches where they can now put up to like a ton or more, or a few tons of equipment on a giant helium balloon. And then they fly around for a month or more and they can stay up. And so it's intermediate between like a space or a satellite experiment or a ground-based experiment. So on the coast, there's a facility called the Long Duration Balloon Facility. So they launch balloons during the summer in there. And so you launch them and then they kind of just circle around rather than drifting off. And then they land back on the continent. You can recover things versus going up, drifting out, dropping in the ocean. And so it's a combination of some unique environmental factors that can't be reproduced other places on Earth, right? And then plus logistical supports that enables you to do that.
Okay, so now let's talk about the Ice Cube itself, or the Ice Cube Neutrino Observatory, which is a research center at the literal South Pole, meaning the very axis of the Earth. Can you tell us anything we might need to know about the Ice Cube and your role there?
Yeah, that's a great question. So I'm now the interim director of the Wisconsin Ice Cube Particle Astrophysics Center, or WIPAC. It's an organization that we have about 75 full-time equivalent employees, and we have multiple projects that we work on, but the dominant one is Ice Cube. The way I like to start, you go like, first, I'm not an astronomer, but here's what I know about astronomy, right? Is look up into the sky and then you try to map what you see. So the first people who did astronomy just used their eyes. Then they developed optical telescopes that allow you to see fainter objects other than like the moon and the planets. You see more details on that, but mostly what you see with the optical telescope is just fainter objects, right? Now, in the last 100 years, we've made instruments that allow us to see things that aren't visible with our eyes. From a physics perspective, there's all different kinds of light. The only thing special about visible light is we can see it without any other instrument. Infrared is another kind of light. Ultraviolet is another kind of light. We now have telescopes that enable us to look for all that different kinds of light. And basically, when you go up to X-rays and then the highest energy light, which is called gamma rays, you learn different things in the same way. If you take a picture of your hand, or if you take an X-ray of your hand, or if you take an MRI of your hand, you see different features. So what motivates people to look at these different types of instruments is to learn something that you can't learn with only one type of telescope. The idea was that these particles called neutrinos would also come from outer space, and they would give us unique information. So in the same way, if I have soft tissue damage, I can take X-rays all day long and it'll never show up. I have to do an MRI. So we're trying to, and have succeeded in making an instrument that allows us to see these almost invisible particles called neutrinos. And then we are going to learn about existing things and then hopefully find more amazing new things that are only visible with neutrinos.
Let's take a minute for some definitions, because there's some words there that are a bit foreign to me and perhaps to some people listening. So I read this about the IceCube project. I'm going to quote now. It seeks to map the universe using neutrinos and explore cataclysmic phenomena like gamma ray bursts and active galactic nuclei that produce neutrinos millions to trillions of times more energetic than those produced in the sun. Let's start with neutrinos. What is a neutrino?
Yeah. So here's how I think life goes is say you meet somebody at a party, right? And you go, what was that person's name? But you don't know anything about them, but you talk to somebody you do know and you go, oh, that, person with the long hair that had the red shirt on and so forth. And then they go, oh, that's Sally, right? And then after a while you go like, no, I know Sally. So we have something that we observe, and then once we have some confidence, then we give it a name. These neutrinos, in some ways, are not any different than an electron. An electron has little parts to it. No matter how much you smash it, you never find anything inside it. So a neutrino is a fundamental particle in that sense. And the role they play is, it turns out particles can change identity. And so you can have fusion that goes on inside the star where you get two protons, that come together and form helium, for example, right? That's an example where there's an identity change. You went from having bare protons to making helium. Same thing happens in radioactive decay, right? You start off with one element, you end up with another element, right? And so, for example, you have radioactive potassium in your body, right? Just naturally occurring. And about 200 million times a day, there's a decay and a neutrino shoots out of you. It also happens if you smash particles together, protons and heavier inside of atoms we call nuclei, there can also be a change in identity and a neutrino shoots out. You may be familiar with conservation of electrical charge. I started off with neutral on one side of my chemical equation. Whatever is formed on the other side needs to be electrically neutral also. But there are other types of conservation laws, and the neutrino is needed in order to satisfy those laws.
Okay, so a neutrino is a particle in the same category of protons, electrons, neutrons. We might call them subatomic particles. and we observe their role in particle reactions of different types. So they're here on Earth, they're coming out of me right now. Why then are we studying the ones from outer space?
Yeah, let me try this analogy on you. It's kind of like if you're interested in the water quality of a stream. One way you could do that is you could say, well, I'm going to measure the pH, I'm going to measure the temperature, I'm going to try to measure, how much suspended solids there are, all those kinds of things. The other thing you can do is you can see what kind of things live in that stream. And for example, trout like really clear, cold water. So if trout live there, you go, oh, that's a healthy stream. So there are people who get really interested in the trout and say, trout are amazing. I want to learn everything there is about the trout. And then there are other people that go like, so much about trout. Now I can learn about where the streams that they live in as an indicator of the quality. So the neutrinos are like the trout, right? We've learned about the properties of the neutrinos. And so when we see neutrinos coming out, then there are people going, that means these things must be true. And the neutrinos versus light that comes from outer space have the advantage that super, super high energies, the neutrinos will basically go through anything. Even though you have this super dense ball of matter, they go right through it just like nothing. And then they can make it through any stuff that's in the way. They can make it through the Earth.
Then they will also travel through ice, which is where your detectors are. And then you have an entire cubic kilometers worth of area to observe these neutrinos.
The downside is because they can get through stuff, they're basically, to a first approximation, invisible. Because you only can see them if they interact with something. And so that's why we need this giant detector in order to measure, just like light comes from, a star or some place where there's interesting things happening out in space, there are neutrinos that come there. And the neutrinos will tell us something unique that either the light can't escape from or the light isn't being produced because we're looking at these super high energies.
Got it. So measuring the strength or abundance of neutrinos with detectors on Earth can give us an idea of a process happening out in space. I also read about this project that it allows us to analyze neutrinos that are up to trillions of times stronger than the ones we encounter on Earth. So I'm wondering if we know why neutrinos out in space are so much stronger than the ones we have here.
That's a good question. And believe it or not, nobody knows the answer to that. What happened was towards the end of the first decade in the 20th century, so the early 1900s, we realized that there were electrically charged particles called cosmic rays that were coming from outer space. But there wasn't an idea of how much energy they had, or there wasn't big enough experiments to look for rare occurrences. Around 1960, there was this particle that detected that had this crazy, like literally more than a billion times more energy than the highest energy particles we can make. So the question has been since 1960, where are those particles coming from and how do they get to such high energies? We measure more of those particles, but the problem is they're electrically charged, they encounter magnetic fields, so their paths get altered. So when they come into your detector, that's not the direction from which they originated from. So you have to find a particle that's electrically neutral that comes from the same spot, and then they'll travel in a straight line. So that's one of the big motivators of neutrinos is they should be coming from the same spots, but since they're electrically neutral, they come in a straight line. And so what we say is they point back to where they originated. So instead of, a weary traveler who's been all over the world, but lost their memory, and so they can't tell you, right? This is one like, no, I came in on this flight. So, oh yeah, I know what your path was.
Okay. So then these neutrinos, they're coming from outer space. We cannot see them with our eyes. Other than for the sake of better understanding the universe and the cosmos, why is it important that we study these things?
Our science is fundamental in nature. So our job is to better understand the universe. So it's kind of like, a professional sports team's job is to win the championship, right? And so you go like, why do you want to win a championship? You go like, that's why we're in the game, right? So our job is to say we have a better way to try to understand the universe than somebody else's. And just like there's so much money for sports, there's so much money, for entertainment, there's things like that. There's money for fundamental research, right? And so we have to say the idea that we have is going to provide more scientific value than some other project. We don't have to say, even though this is counterintuitive and question I get most often, why are you doing this, right? The answer is to better understand the universe. And then people always say, but will this lead to a new energy source, or will this, for most people, that statement doesn't have much meaning. What does that mean to better understand the universe? But in our realm, that's what we have to deliver. We have to say, we're going to build this instrument. This is the types of things that it can explore. This is how capable it will be. And then we believe, that this is a good investment for the science dollars that we have.
I think that's a great answer. And this podcast is definitely a safe space for appreciating the value of research for the sake of knowledge. I am also just curious, so I'm going to ask you, does this research have any applications for something that's on Earth?
Yeah. So it turns out the types of skills that are needed to make the project succeed are widely transferable to a range of things, right? One of the interesting things is initially when IceCube was proposed, people said, I don't care if you can make sensors that will survive. I don't care if you can somehow get all the material to Antarctica. Put those sensors down on the ice. They said, there are so many other things happening. You won't find the neutrinos. There's only a few hundred from outer space every year out of 100 billion. So now how do you sort through that much data and not lose the ones that are important? Those skills are important for a wide range of problems.
Okay. Yeah, I think a lot of emphasis gets placed on sort of results or answering the research question, which, is understandable, and that's also what you're doing. But there's also a lot that can be learned through the process of perfecting a methodology or developing techniques, which is part of science and also a big fundamental philosophy of what science is. We are going to start to round out the episode, and so I want to ask you if there is anything else that we didn't talk about today that you think is important to add or mention in the discussion about astronomy or astrophysics in Antarctica?
Yeah, I think the fundamental science, I always say a little bit provocatively, if you give passionate people some freedom to do what they like, once in a while, just by accident, they discover something that's useful, right? The issue is you can't just go, let's only fund applied research, because at some point you exhaust the capabilities of what you know. So pushing the frontiers, I think aids everyone, but mostly, it's a great to live in a time where we have enough resources that we can do things that beyond our immediate needs.
I think that's a great answer. Next, I want to ask you, what is your favorite thing about conducting research based in Antarctica?
That's also a great question. You could probably look for your podcast and you say, who would I like to talk to, right? And there are people doing all kinds of really cool science, and they all believe their science is so cool. But it's a great hook to say, I work in Antarctica. Everyone I work with, and there multiple times, right? And so the other kind of fun thing is now, because I've been involved in this project so long, so now I can stay. I've given an IceCube talk on every continent.
Yep, that's definitely a pretty cool job you've got. The last question is, where can people find you and follow your work and the work of the IceCube?
Yeah, I would point you to the IceCube webpage, so icecube.wisc.edu. But if you just Google IceCube, depending on when you do that, sometimes if you do IceCube and neutrinos, we always come up first. Usually we come up either first or second with IceCube wrapper. And then we have social media channels. So, we're on X, we're on Instagram, we're on Facebook. And then, my contact information would be there.
All right. Well, listeners will be able to find all of that in the episode description. And this is the part where I say thank you for coming on the show today. Thank you for teaching us about neutrinos. And thank you for your research and helping us understand the universe better.
All right. Great to talk to you, and thanks for reaching out.
Okay, a major thank you to Dr. Jim Madsen. And now I'm going to ask you listeners to tell me if you enjoyed this episode, because if you did, I'll make more like it. Today we did astrophysics, and so we will at least have one more on astronomy. But both are pretty large fields, and even though it might not come to mind right away when we think about Antarctica, there's a lot of cool stuff happening down there that we can get curious about. So yeah, leave a comment on the Spotify app or reach out on socials, and we'll keep doing episodes like this. All right, that's all I have for you today. Thanks a bunch, and we'll talk soon. You've been listening to South Pole. You can find more information about this week's guest and links to their work in the episode description. Cover art for the show was done by Laurel Wong, and the music you're listening to was done by Neela Ruiz. I am your host, Clark Marchese, and this episode was produced and engineered by me. So if you found it interesting, send it to someone you know. South Pole is part of a larger network of science-y podcasts called Pine Forest Media. We've got one on plastic, one on drinking water, and a couple new ones coming out soon. So you can find more information about us in the episode description as well, or on our website at pineforestpods.com. We're also on Instagram and TikTok at Pine Forest Media. If you love the show and you want to support science communication like this, a 5-star rating across platforms and a review on Apple Podcasts is one of the best things you can do to help us reach more people and for the entire network to grow. All right, thank you to all of you who have made it this far, and we'll talk soon.